So we're saying that right in the center, in a very tiny space, very tiny volume, we have protons and neutrons. Okay, and in the rest of the space, what we are gonna find will be electrons. Okay, so electrons, electrons are divided in shells, or occupying shells, right? And we talk about shells being quantized, meaning that they have a very specific value of energy, so the energy doesn't jump, so doesn't grow continuously. So there are jumps of energy levels from one electron, from one shell to the next shell, and so forth, right? So we also discuss here the maximum number of electrons that can be found in any given shell. Anybody remember what's the formula for that? How did we calculate? Okay, 2n squared. So thank you for that. That's beautiful. So based on that, we agree that in the first shell, how many electrons can be found in the first shell? 2 electrons, that's good. What about shell number 2? What's the maximum number of electrons that we can find in shell number 2? Great. And what about shell number 3? 18, right? Good. So that's good to remember. We also talk about the shells subdivided in subshells, correct? And we call these subshells orbitals. Okay. So remember how we define now orbitals as the region in the space where a maximum of 2 electrons can be found. Remember that, okay? And based on that, so the maximum number of electrons found in an orbital is 2. I'm gonna write here 2 electrons so everybody remembers that well. And based on that, how many orbitals can we find in shell number 2? Okay, so in shell number 2, the maximum number of electrons is 8, right? Because it's 2n squared. 2 squared, 2 is 4, times 2 is 8. So 8 is the maximum number of electrons that we can find in shell number 2. And I'm emphasizing, guys, shell 2, remember, we're talking about the element of the second period of the periodic table. So shell number 2, maximum number of electrons is 8. Orbitals, 4. So what are the orbitals that we can find in shell number 2? So we said 4 orbitals, and those orbitals are what? Guys, remember that. Oops, sorry. So we can find in shell number 2 4 orbitals. One of these orbitals is an s orbital, and 3 p orbitals, correct? So that's, and remember how we discussed that the s orbital is slightly lower in energy as compared with the p orbitals, and the p orbital being degenerate orbitals. So they have the same, exactly the same level, okay? Um, so 3p orbitals having the same energy, they are degenerate orbitals, and I'll type it on the chat just in case. That means that they have the same energy level. And slightly below, we have the s orbital. We also discussed and I am repeating this because of how relevant it is for the class, okay? Uh, the s orbital is a sphere, right? This is the shape, it's a sphere, and the p orbital, anybody remember what's the shape of a p orbital? What are we expecting of the shape of a p orbital? Good, so dumbbells, lobe, perfect. Something like this, correct? So we have three p orbitals, okay? Beautiful. And these three p orbitals, what is the angle in between the three p orbitals? So we said in the last class that the p orbitals are orthogonal, okay? And that means that there is a 90-degree angle in between the three p orbitals. I drew in the previous class. And the last thing that I said also was that, remember guys, I want to also emphasize this. Well, before I go, one second, let me finish here. So this is the three p orbitals. They have a 90-degree angles between them. Remember, you can picture them as axes X, Y, and Z in math. That's exactly how they're going to look like in space, the three p orbitals, okay? 90-degree angles between them. That's very important, guys. It's very relevant. And you will see why very soon, okay? So the s orbital is in a sphere. I'm gonna say this is a 2s, and the p orbitals, they are dumbbells. They are orthogonal, meaning that there is 90-degree angles in between them, okay? Once again, each orbital can have a maximum of 2 electrons, and then we also learned in the previous class how to fill up energy orbitals for electrons, starting from bottom to top, adding 2 electrons per orbitals, and when you have degenerate orbitals, you add one at a time in the orbitals with the same energy level. We practiced some problems in regards to that. So we also discussed in the previous class, and I'm going to rewrite it here again, how electrons have wave properties. So they behave as a wave, and that's a really important something that, and because of this, because of the wave properties of electrons, then we said that we never talk about an electron being here or an electron being there, but we rather refers to electron density when we talk about orbitals. So if we have 2 electrons in orbital s, we are not going to think that inside this sphere there will be 1 electron here, one there. No, there will be electron density in the whole orbital accounting for 2 electrons. If we think about a p orbital, then it's the same thing, right? So it's going to be electron density in the p orbital, right? Set here. So and that right at this point, the electron density is 0. Anybody remembers how do we call this point with 0 electron density? All these things we discussed in the previous class. Okay, it's a node. Okay, it's a node, and there is a nodal plane too. Okay, so I'm gonna call this 0 electron density, and that point, that's a node. I want you guys to be familiar with these concepts. Okay, uh, and another thing that I emphasized in the previous class was the fact that this p orbital have different shading. Anybody remember what that the shading in the orbital refers to? That's another really important thing. Anybody remember what the shading refers to? The sign of the wave function. Beautiful. So the shading refers to the sign of the wave function. So when we look at the p orbital, we are talking about the sign of the wave function here having a being positive or negative, and here the opposite, right? So it's not that there is electron density here and here there is nothing. No, there is electron density in both lobes, right? And the shading only refers to uh, the sign of the wave function. That is beautiful. Okay. So with that ideas in mind, guys, and that's I'm very happy to see that quite a few people remember that. If you don't, please rewatch the lecture or this brief summary because it's very important for you guys to understand this. Something that I also want to repeat because of the importance of this concept is we also refer to electronegativity, a key concept in this class, electronegativity. Anybody can type on the chat what is electronegativity? How do we define electronegativity? What's the definition of electronegativity? Yeah, you can say with your own words. So, is the power of attraction for the electrons in the outermost shell. That's beautiful, Ryan and Harry, and so that's the real concept. So, the power of attraction of an atom by for the electrons in the outermost shell. That's how we define electronegativity. The stronger the attractions, right? The more electronegative the atom will be. So if we think about electronegativity and we think about a period from in the periodic table from left to right, what happens with electronegativity from left to right? It increases, okay? And why does it increase? All these things we discussed before, but I want you guys to really remember. Anybody remember can type in the chat why does electronegativity increases on the period from left to right? What's the reasoning behind that? Okay, so from left to right on the periodic table guys, what happened? So let's go back to another question so you can reason this. When you look at the group of the periodic table, what information is that telling you? If an element is in group 4, what is that telling you? What kind of information will give you that? It has four valence electrons, right? So the group number equals the number of valence electrons. What about the period number? Equals what? Exactly, the valence shell. The number of shell of the valence shell, right? You're gonna write the valence shell. So for atoms in the second period of the periodic table, the valence shell is shell number 2, right? For atoms in the third period of the periodic table, valence shell will be shell number 3, and so forth, okay? So if we compare electronegativity, I'm sorry, from left to right, and we are talking about the same period in the periodic table, that means that every atom in the same period have the same valence shell. So if we think about, for example, period number 2, right? So we are talking about all these elements in period number 2 having the valence shell will be shell number 2, okay? So from left to right in the periodic table, the number of protons increases. So from left to right, I'm gonna say here, shell, valence shell is the same, number of protons increases, okay? Therefore, if the valence shell is the same and the number of protons is increasing, the attraction, because you have more positive charge on the nucleus, in between those positive charge and the outermost shell electrons, in this case the valence electrons, the attraction will be stronger because there are more protons and more electrons. Even though for every element in that sequence in the same period, all these electrons are in the same shell, shell number 2. So that's why from left to right, the power of attraction is stronger. So more attraction by the valence electrons because there are more protons in the nucleus. And every atom there will be having the same valence shell. Is that okay? If anybody has a question, please type it in the chat or let me know. And what happened with, again, all these things we discussed in the previous class, but this is a good uh, reminder. So what happened in the group of the periodic table from top to bottom with electronegativity?
Decreases.
It decreases. And why does it decreases? What happens in the group for from top to bottom? What happened from top to bottom in the periodic table? Aha. Okay, from top to bottom, the number, that's beautiful, Haritha. So the number of shells increases. So if you go from period 2 to period 4, we are going from shell 2. So the valence shell goes from being 2 to 4. So meaning that the electrons are farther and farther from the nucleus. The size increases when you go from top to bottom in the periodic table. And because the size of the atoms increases so dramatically, and then the valence electrons will be farther away from the nucleus, then obviously electronegativity will decrease. Okay, that's very important, guys, to keep in mind. As I said in the previous class, these are concepts that you will use a lot in this class and in organic chemistry as well. With that in mind, then we can say what is the most electronegative atom of the whole periodic table? According to this reasoning, fluorine would be the most electronegative atom, correct? That's beautiful, okay? All right, guys. So with this in mind, I'm gonna continue reviewing things that we did in the last class, and then bringing some new ideas to today's class. And so with this in mind, we also discussed in the previous class something called uh, Lewis structures, right? So how do we draw Lewis structure of atoms? Did we or we didn't? Believe we did go over Lewis structures. If we did not, okay, good. So how do we draw Lewis structure of of single atoms? So let's say I'm gonna draw the Lewis structure of the atom of fluorine. What should I do there?
Do we use the valence electron information, right?
Right. You need the so what you need to know is in which group of the periodic table is this element located. That is gonna tell you the number of valence electrons, and then you're going to add the number of dots, which will equals the number of valence electrons. Fluorine is in group 7, so if we're going to draw the Lewis structure for an atom of fluorine, we are talking about adding 7 dots, okay, because there are seven valence electrons in fluorine, and that you can apply to any other atom of the periodic table. Good. And we also went over the octet rule, which I'm gonna write over here. So one question I got here, does it matter how electrons are placed? For now, it doesn't matter. You get used to, because we're gonna focus mostly on doing Lewis structure of molecules, not really atoms. So it really won't be a big factor. Okay, so don't worry too much about that now. We talk about the octet rule as well. Anybody remember what is the octet rule? What does it tell you? Okay, so remember the origin of the octet rule is noble gases are highly stable, right? And the one thing they all have in common is that they have a full valence shell. So the valence shell of every single atom that is considered a noble gas in group H is actually full, right? And they're highly stable. So that actually made scientists to think, what do they have in common? Obviously, that's what they have in common, a full valence shell. So atoms will react in such a way that they will tend to complete the valence shell, right? In the case of the element of the second period, they will react in such a way to complete, and I'm gonna say this for, once again, period number 2, complete A electrons in the valence shell. And we're focusing on period number 2 a lot because once again, that's where carbon is, nitrogen and oxygen. And remember how we care so much about these elements because this is a class which is a pre-orgo class. And organic chemistry is a chemistry of carbon, right? So atoms tends to react when they're forming new bonds by completing A electrons in the valence shell. And that brings me to bonding. So we discussed in the previous class um, a little bit about bonding, and in particular, and I'm gonna go back to that again. We talk about ionic and covalent bond. That was at the very end of the class. Okay. So for a few minutes now, what I want to do is a small problem with you guys. I want everybody to do the electronic distribution of the, I'm gonna give you now, of, let's say, uh, magnesium, for example, let's say sodium. So I want you guys to do the electronic distribution of sodium, and the atomic number of sodium is 11. Okay, so let's write the electronic distribution of sodium in your notebooks. And if anybody who wants to type it on the chat, feel free as soon as you're ready. Feel free to type it on the chat. What's the electronic distribution of sodium? If the atomic number is 11, what information can you get out of that? So what is that telling you? Atomic number equal 11. So the atomic number equals what? Equals the number of protons, which is 11. So there are 11 electrons. That's good. So there you go. So two answers, and they are both correct. So we're talking about 11 protons, so 11 electrons. So that would be 1s2, 2s2, that's 4 electrons, 2p6, that is 10 electrons. So I need one more. I'm gonna go to level 3, shell number 3. 3
3 is
plus
1.
1, correct. Right. So that would be the electronic distribution of sodium. Beautiful. I'll take the question right now. Give me 1 second. You can write 2p6, but if you write 2px2, 2py2, and 2pz2, that would be even better. I could accept both answers, but it would be better uh, if you do that. Then another thing that I want you guys to do is uh, um, to write the atomic distribution of chlorine. Atomic number is 17. So as soon as you guys finish it, just type it in the chat. The electronic distribution of chlorine atomic number is 17. Okay, so that's good. So we're talking about now, once again, 17 electrons, right? So I'm gonna just copy and paste this to make my life slightly easier. Now right here. So that could be, so 1 is 2, 2 is 2, 2p6, that's 10, 3 is 2, that's 12, and then 3p5, that would be, right? So, just to make sure, so just to check, fluorine valence shell is 3. So you can see how that matches with my electron distribution here. And the number of valence electrons is 7. So that's beautiful. Sodium is in group 1, third period. So that's perfect. So we discussed in class that whenever, and I'm gonna also give you another piece of information that is gonna be useful. So the electronegativity of sodium is 0.9, and that of fluorine. I'm sorry. I made a mistake here. You guys did not correct me. We're talking about chlorine, not fluorine. Okay. 3.0. Okay, so that's a quite significant difference in electronegativity, right? So we talk about when two atoms had, so the first thing that we need to, so when we bring together an atom of sodium and one of chlorine, the first thing we want to do is look at the difference in electronegativity in between these two. Difference in electronegativity here is, and I'm gonna write a symbol. Let's see if I can find it. Here it is. So difference in electronegativity equals 3 minus zero point 0.9, that equals 2.1, right? So we said in class, in the previous class, that any two atoms with a difference in electronegativity larger than 1.9, a bonding in between these two atoms will always be ionic, okay? So when there is a quite significant difference in electronegativity, okay, in this case, 2.1, so whenever it is larger than 1.9, the resulting bond is an ionic bond. Okay, so ionic bond, and why is that the resulting bond? So because there is a transfer of electron. Um, that's a good question. Electronegativity, there are different scales of electronegativity, so but no units. Okay, for now, no units. You can find certainly different units of, because they are relative. The reason why no units is because they are relative to fluorine. So they assign the value of 4 to fluorine, and then every atom is relative to that. So it's a relative measure. Uh, so guys, so there is a transfer of electron. So if we have 1.8, it's almost ionic. So remember, things are not white or black. It will be, we'll go over what is it right now, but it will have a, I would say the answer to that root could be that bond will have a high ionic character. So we will talk about ionic character instead of that. Okay. So go ahead, Ruth. You're gonna.
I have another question. Does it also have to do with metal and non-metal?
It has to do with that, but once again, but to classify them in metals and non-metals, which you can do, uh, it's kind of memorizing. So I want you to understand why it's a metal, why it's a non-metal, and focus more on the electronegativity and the reasoning behind this. Okay.
Okay, thank you.
So in this case, we have a difference in electronegativity of 2.1. So clearly that's an ionic bond. And guys, I'm gonna write it over here because that's transfer of electrons. So whenever we talk about ionic bonding, then electrons are being transferred. In this case, and not in this case, always the electrons obviously will be transferred from the lowest electronegative atom to the highest electronegative atom. And I'm using here what I said is a curved arrow, something we are going to use in organic chemistry a lot. So that, and in this class too. First time we are using this. So I'm using the curved arrow to indicate, and this is half an arrow. You can see here on the head, because we are transferring only one electron, right? So uh, by this electron transfer going from the lowest electronegative atom to the highest electronegative atom, I'm showing that the curved arrow is departing from the electron source, meaning that from wherever the electron is departing, that's where the arrow departs to. And the arrow ends wherever the electron is ending. It's a very simple concept, but then later, once we see molecules and different bonds, it will be more complex. That's what I want to introduce this idea with a simple example as this one. So curved arrow departing from the electron source, in this case, is these electrons from the lowest electronegative atom, ending on whoever is receiving that electron, in this case, the highest electronegative atom. So now, if sodium loses one electron, then the electronic distribution now will be this. And in that case, um, what's going to happen with the sodium atom? If the electronic distribution is now 1s2, 2s2, and 2p6, what's going to happen with that? Did something change? It lost one electron. So if it loses one electron, what's going to happen with sodium? It will be coming into a cation. So it's going to become into sodium cation. It becomes into an ion. Okay, that's the definition precisely of an ionic bond. Okay, so it loses one electron. And guys, I'm going to introduce something here, another concept. I'm going to type it on the chat. It's called formal charge. And the formal charge is the charge of an atom in a molecular ion. Okay, so sodium turns positive. It becomes into a cation because it loses one electron. And then chlorine, which accepts this one electron, obviously will become negatively charged. It has an extra electron. Now it has 2p6. And that would be a perfect situation because, as you can see, uh, the sodium atom is left with a full octet, and the chlorine atom is also having a full octet. So they are both with full octets. That's why they can form this very stable compound that is sodium chloride uh, or table salt, which you use at home every single day. Okay. So remember how I said in the previous class, ionic bonds, once again, transfer of an electron from the lowest to the highest electronegative atom. We are talking about transferring electrons, therefore, um, the charge, we're going to be creating ions, and therefore, the bonding in between these ions is going to be very strong. It's the strongest of all of them because you have full electrical charge here. So that's why if you try to melt sodium chloride at home, it's going to be quite impossible because the forces of attractions in between the negative and positive charges is very strong. So it will require a lot of energy to break this down. All right. So that's one of bonding that I wanted to that we learned in the previous class. But again, I wanted to repeat this because it's so important. And then we also talk about cases in which, for example, let's say, and now I'm going to use Lewis structures. Let's say we have a chlorine atom here, and if we are going to do Lewis structure, we will be adding how many dots to chlorine? It's in group 7, so that would be 7 dots. Mhm. So if we react with two chlorine atoms, they both have 7 electrons in the valence shell. So what I'm going to do now is I'm going to write it this way to show you this better. So now in this case, to form the bonding in between both chlorine atoms, so they both need to add 1 electron to the valence shell to complete 8. So what I'm going to do to use the curved arrow is just to indicate that this 1 electron will be from here, and this 1 electron will be from here. Sorry. And by expressing this, I'm showing that a new bond is going to be formed. Okay. And that's going to be a chlorine molecule. We use a line to indicate this bond, right? And this line means that there are 2 electrons here for the bonding. And I'm going to complete now the Lewis structure. Okay, so now in this case, okay, we have a bond in between 2 atoms. So once again, by means of this reaction function, you can show the electronic distribution here. What's happening here is they are actually giving 1 electron each to form a bond. In this bond here, electrons are shared. And the moment we share electrons, talking about covalent bonds. Okay, guys, so that's once again big difference. In ionic bonds, electrons are transferred. In covalent bonds, electrons are shared. In this particular case, because um, the electronegativity of both atoms clearly is the same because it's the same atom, we're talking about a non-polar covalent bond. Okay. So whenever you 2 atoms react and they don't share, there is no transfer of electrons, but electrons are shared, the result of this bonding is going to be a covalent bond. and if the difference in electronegativity in between these two atoms is below zero point 0.5, then we will be talking about a nonpolar covalent bond. I'm gonna give you some examples here. For example, the bond in between carbon and hydrogen, and I'll give you now the specific electronegativity values. So electronegativity of carbon is 2.5 and hydrogen is 2.1. So difference in electronegativity between these two is 0.4. So that's a non-polar covalent bond. So exactly what, when you guys look at this, what I want you guys is to envision what exactly this means, okay? It means that the electrons in a non-polar covalent bond are pretty much equally shared in between both atoms, okay? That's exactly what it means. Now, there could be a situation in which um, goodness, no, 1 second. So there could be a situation in which instead of sharing both, and I took away I'm gonna open a new page, I'm sorry. So instead of sharing the electrons equally, the electrons are shared unequally, meaning that one of the atoms attracts more the electrons than the other one. So there is a significance in difference in electronegativity, not as big as to make it ionic, but let's say, for example, if you have the atom of carbon bonded to the atom of oxygen, and I'm gonna, 1 second. So the program is smart because it knows that the carbon must have 4 electrons. That's giving me a warning that I'm doing something wrong. So I'm gonna give you the values of electronegativity for both carbon and oxygen. Okay, so carbon we said is 2.5 and oxygen is 3.5. Okay. So better now? Okay. So guys, so here we have a bonding in between carbon and oxygen. Okay. So electronegativity of carbon is 2.5. Electronegativity of oxygen is 3.5. So the difference in electronegativity here is 1, which actually means that we're talking about a polar covalent bond. So it means that it's a bond which is polarized. A polarized bond means that the electrons in that bond are not equally shared. So they are attracted stronger by one of the atoms as compared to the other one. So when do we have a polar covalent bond? When the difference in electronegativity is in between 0.5 and 1.9, okay? So somebody was asking me, what if I have a difference of 1.8? So if you have a difference of 1.8, it's still a polar covalent bond, but it's gonna have a very high ionic character. The closer it is to 1.9, obviously, the more ionic the bonding will be. Still will be a polar covalent bond though, okay? So guys, when we're talking about a polar covalent bond here, And we are telling you here that the oxygen is more electronegative than carbon. We know this. They are both in the second period of the periodic table. And oxygen is in group 6 and carbon on 4. We just talked about electronegativity decreasing. I'm sorry, increasing. So what happens here is the bond being polarized means that one of the electrons of this bonding will be closer to one atom, in this case, the most electronegative atom, which is oxygen, okay? So that actually means that because the electrons are not equally shared, okay, there will be a partial negative charge over the oxygen, meaning a fraction of negative charge over the oxygen, and this fraction of negative charge is resulting once again from the polarized bond here, meaning that these two electrons are closer to the oxygen. That's giving the oxygen an excess of electron density, right? And an electron deficiency in the carbon, because once again, the bond is polarized toward the oxygen, okay? So we also use sometime in chemistry, some textbooks, you can use an arrow to show the bond is polarized toward the oxygen because it's more electronegative. And the point being is, the program continues to do this. It doesn't like that I'm drawing the carbon just like that. So what this means is actually, once again, a difference in 0.5 and 1.9, so a difference of electronegativity leading to a polar covalent bond means exactly what I'm showing on the screen right now. The electrons of this bonding will be closer to the most electronegative atom, to the highest electronegative atom, in this case oxygen. And that is going to create a fraction of negative charge over that atom, and obviously a fraction of positive charge over the atom which is less electronegative. Guys, this is quite simple, but it's actually super important because that's really the foundation of many of the reactions that you will learn in organic chemistry later on, okay? So whenever you have a bonding in between two atoms and the difference in between both of them is in between 0.5 and 1.9, that bonding will be classified as a polar covalent bond, okay? So I'm gonna give you now another example. Well, any questions so far in regards to this? No more questions? Okay. All right. So before we go in to do more examples of this, uh, so as a summary, guys, we have, okay, so Ruth had a question. Go ahead.
No, no, just like I was taking notes. Whatever we have just said, between the range 0.5 and 1.9, we have the polar covalent bond, as it is shown over here, right?
Correct.
Okay, thank you.
Right. So, um, so we care about this a lot because this is the foundation from the reactions in orgochem, as I said before. Okay. And so, as a summary of this, guys, for now, because soon we're going to learn some more, we can say that we can classify the bonds as ionic, polar covalent, and non-polar. Okay. And now you know that you can classify the bonding. This classification comes from where? From the difference in electronegativity in between the atoms forming that bonding. All right. With that information, now, when you look at a molecule, you should be able to tell exactly what kind of bond do you have in that molecule. Okay, so that brings me to something really important that we are going to be learning today, uh, which is we're going to learn how to draw organic molecules. Okay, so um, this is something that is it's really important because when we study organic chemistry, it really there is really not much time for students um, to learn to go over in class on this. Once again, that's the point of having this Chem 2110 class, so you can learn all these things before you go to organic. So the organic molecule, organic chemistry is the chemistry of carbon, right? So before I'm going to show you how to draw organic molecules, I want to ask you one simple question we learned in the previous class. What is the maximum number of bonds for the carbon in any molecule?
4.
4. Okay, that's beautiful. There are a lot of people are answering that. Why is that? Why is the maximum number of bonds? Nope, it's not because of that. So why is that? What is the valence shell of carbon? Carbon is in the second period of the periodic table. So what is the valence shell of carbon? Shell 2, right? How many orbitals do we have in shell number 2? 4 orbitals. Okay, so there could be a maximum of 4 bonds. There are no more orbitals for more bondings. So I don't want anyone ever to draw a carbon with more than 4 bonds. You can find a carbon with less than 4, and we will see that. But never ever a carbon with more than 4 bonds. Okay? So organic chemistry is the science of carbon chemistry because um, simply carbon has this ability of forming very stable molecules in which you find carbon atoms bonded to other carbon atoms. All right. So the first thing that we are going to do is we're going to learn a few ways of drawing an organic molecule. I'm going to start by drawing the simplest organic molecule that you can find, which is called methane. I'll type it now. We'll get into shapes later on. Okay, sorry. So as I said, the maximum number of carbon bonds is 4. And guys, something that also going to be doing now, I'm going to start drawing Lewis structures of molecules, okay? Uh, okay, so this is the structural formula of methane. I'm going to write the name over here. 1 carbon with 4 bonds, and obviously hydrogen is the second most important element in organic molecules, and the second most common element in organic molecules, okay? All right, so this is a simple molecule. You can also draw methane in something we call condensed formula, which is CH4. Okay, so you can draw methane as CH4. That's what we call, once again, um, condensed formula, or as a full structure, the Lewis structure. We're going to call this Lewis structure, okay? I'm gonna call this Lewis structure. Everybody remembers. And this is gonna be condensed. Okay, so that's simple for methane. Then the next molecule that we can show, the next in terms of complexity is going to be, instead of having one carbon, the molecule having two carbons, that's going to be a Lewis structure, would be this. Now, the condensed formula for this molecule will be CH3, CH3. The the number 3 is subscript, okay? That's called ethane. Any questions so far? So far so good. Every carbon having 4 bonds. Look here, so this carbon is bonded to one carbon here, okay? Okay, that's a good point, Kevin. So is it wrong to send C2H6? So that's a very good point you made. I'm gonna add this here because I didn't do it for methane since it's so simple. So C2H6 is the molecular formula. Okay, so thank you for reminding me that. Okay, that's a molecular formula. It's a different thing to the condensed formula. Okay, obviously for methane, the molecular formula is the same as CH4. This is the simplest of all organic molecules. Okay, now for ethane, the molecular formula is C2H6, and the condensed formula is CH3CH3. All right. Now that, so once again, this carbon is bonded to one hydrogen here, another one here, another one here, another carbon here. So they're gonna go next to another, the next molecule here in order of complexity will have now 3 carbons. And again, guys, the point here is I'm hoping you guys, everybody is at home drawing this in the notebook. Draw this in your notebooks. It's going to be very helpful. Now, the condensed formula here will be CH3, CH2, CH3. Okay? So when you write condensed formula, guys, and this is how you will see a lot of different textbooks, okay? Everybody, when it's looking at this written formula, everybody knows that the carbon here, this carbon is bonded to this carbon, and this one is bonded to this one. So it's a carbon chain, okay? Everybody knows this. That's the point of a condensed formula. The molecular formula is a different thing because it doesn't tell you which carbon is bonded to which, okay? That's C3H8. Uh, Go ahead, Ruth.
So basically, in order to identify this, the condensed formula and the molecular formula is that condensed formula describe, right, which one belongs to which, and like it gives basically more details. Let's say that.
Exactly, that's the point. it gives you more details on which carbon is bonded to which. How is the carbon chain? For propane, this with three carbon is very simple. I'll show you an example now where you will see how different could it be. And and more importantly, I'm gonna add something new here, which is uh, something we call in organic chemistry, which is the way that something that actually the most common way of drawing organic molecule, line and angle notation. That's the name. I'm gonna add it over here. Okay, I'm gonna find another color because obviously, well, okay. So what is line and angle notation? Remember how I said guys that a line means a bond, right? So I was showing you the molecule of CO, and this line here was a bond of 2 electrons, right? So we're going to use that same idea, but for organic molecules. Now, in this case, we are going to draw the molecules in zigzag, okay? Zigzag carbons. The name of the 3 carbon molecules is propane. I'll write it over here. Guys, look at this. Um, so, a few things about line and angle notation. You draw the carbon chain, the carbon is backbone of the molecule as a zigzag lines, okay? So as many carbons as you need, this is a carbon chain, okay? Each intersection of these 2 lines, whenever you see a vertex right here, that's a carbon. And the ends of the draw, those are also carbons. So in propane, we have 3 carbons, 1 carbon here, 1 carbon here, and 1 carbon here, 3 carbons. In this molecule that I do here, we have 1, 2, 3, 4, 5, 6 carbon. In line and angle notation, and I'm gonna write it once again here, intersections are carbons. No need to draw hydrogens. Everybody knows, everybody knows that the maximum number of bonds for a carbon is 4. Okay, so we don't draw hydrogens in line and angle notation. This carbon right here in the center, how many hydrogens do I have in that carbon? The one that I'm pointing out here on the slide. Okay, two hydrogens, because this carbon is bonded to 1 carbon here, that's one bond. 1 carbon here, that's another bond. So it has 2 bonds, meaning that it's missing 2 bonds. Those 2 bonds must be hydrogens. How many hydrogens in this carbon here on the end carbon? 3 hydrogens. Beautiful. Okay. All right. So I'm gonna continue now and give you another example. The next molecule will be 4. That will be the Lewis structure. The condensed structure would be this one, right? CH3, CH2, CH2, CH3. Some textbooks can also use this notation as the condensed formula. I'm going to show you right now. So they just add parentheses and so this is another way, okay? You can show parentheses 2, that means 2 CH2s, okay? Either is valid. Molecular formula here would be C4 H10, and the line and angle would be this. 4 carbons, CH3, CH2, CH2, CH3. Any questions? Butane. You don't need to know the names for now, okay? We'll learn nomenclature in organic chemistry later on. Because these are simple common names, but then once they get more complex, you'll need uh, to know nomenclature, rules of nomenclature to name the compounds. So that next semester. So all right, so now I'm gonna show you this, okay? So this is a molecule with 4 carbons. However, I have that is potentially another way to draw an organic molecule with 4 carbons, which could be this one. So let's say look at this other molecule here. So here, give me 1 second, okay? So here we can say this molecule will be, the condensed formula will be CH3, CH, and then, so we're gonna assume for the condensed formula that it's a main carbon chain here, and then attached to this main carbon chain there is a CH3. So I'm gonna set CH3, CH, parentheses, CH3, CH3. Okay, so basically you put in parentheses here anything that is attached to the main carbon chain. We'll practice this more in the next class, but still we have time today. But I just want, so we have CH3, CH, parentheses CH3, CH3. The molecular formula here is C4H10. And now the line and angle, it is necessary. The parentheses, because that's how you tell where is the CH3 attached to, okay? Because by doing this, you're telling people that this CH3 in parentheses is attached to this carbon over here, okay? not in the, so the parenthesis means that whatever is inside the parenthesis is not in the main carbon chain. The main carbon chain is this one. It's something that is attached to the main carbon chain. That's why parentheses are a must. And if you were to use line and angle, this could be the picture. CH3, 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 and here there is only one hydrogen, it's a CH, because it's bonded to 3 hydrogens. Okay? So, I want you guys then to understand, we're gonna do some more practicing now, but I'm gonna give you some other piece of information. So we have here the Lewis structure, full structures. We can also call these full structures. Condensed formula in which we write in the parent carbon chain, the main carbon chain, and we put in parentheses anything that is attached to the carbon chain. We have molecular formula, which is the number of atoms composing this molecule, in this case, 4 carbons and 10 hydrogens. The atoms and the number of these atoms that are forming this molecule. And very important, the line and angle notation, in which we will use a line to show a bond. We're gonna draw, I'm gonna add it over here. Carbon chain, show a zigzag. Draw, okay. And we don't need to draw hydrogens. And then we know that every intersection of these two lines is a carbon, and the ending of the lines are also carbons. That's the line and angle notation. Okay. Any questions? All right, so let me give you something else. So now what I'm going to do is, before I continue, I wanted to add something here. Okay, these last two molecules, um, you can see how they have the same molecular formula, but they have different structures. So the same molecular formula, but they have different connections in between the carbon atoms. The carbon atoms are connected here differently as they are connected here. So different same molecular formula, different connectivity in between the atoms. Two different molecules, we call them isomers. Same molecular formula, different connections in between the atoms, isomers. Two different molecules, different chemical and physical properties, okay? We call them isomers. All right, so let me give you now I want these two molecules, guys. I want you guys to, this is a problem, okay? So let's draw for these two molecules. A molecular formula. B condensed formula. So what is the molecular formula on, I'm gonna call this molecule A, this is gonna be B. So what's the molecular formula for molecule A? Type it on the chat. So remember molecular formula, Alexis, that's the condensed formula. So molecular formula is how many carbons total in this molecule? In molecule A, how many carbons? 6 carbons, right?
Yeah, 6 carbons.
So that's C6. So 1 carbon here, 2, 3, 4, 5, and
12.
6. And then hydrogens, how many hydrogens here?
12.
How, how many hydrogens in this ending here? In the end of the carbon chain, how many are hydrogens here in this position?
Isn't it 12?
No, I'm asking in the 3 hydrogens, right? In this position here, how many carbons here? How many carbons here? Right here, 1 carbon. And how many hydrogens right there? How many hydrogens here? 3 hydrogens, right? So 1 carbon, 2 carbon, 3, 4, 5, 6. That's okay. So 3 hydrogens and 3 hydrogens here is 6. How many hydrogens right here? 1 hydrogen, because this carbon here is bonded to 1 carbon to the right, another one here that's 2 bonds, another one here that's 3 bonds, and what is missing is 1 bond, so there is only 1 hydrogen. 3, 6, 1 is 7. How many hydrogens here? 1, that's 8. How many here? 3. And how many here? 3. So how many hydrogens total? Once again, 14 hydrogen. 3, 6, 7, 8, 11, 14. Condensed formula. The carbon chain, I'm gonna color code the main carbon chain. The main carbon chain is the longest carbon chain. In this case, I'm gonna pick this one. It doesn't matter in this case because it's the same, but it's the longest carbon chain. Is the main carbon chain. So that's correct, Fariha. So it would be CH3, CH, parenthesis CH3, CH, CH3, CH3. Or I'm gonna give you another option that you can also find in textbooks. I will accept this, no question about it. But you can also write this as it follows. CH32, CH, CH, CH32. So CH32, CH, CH, CH32. Okay, good. What's the molecular formula for for molecule B? How many carbons do we have in molecule B total? 6 carbons, right? One, two, three, four, five, six. How many hydrogens we have in this molecule B? So how many hydrogens here, guys, in this position that I'm pointing in the screen now? How many hydrogens do we have there? No hydrogens in that position. Okay, so the total would be 3, 6, 9, 0 here. How many here? That's 2, 11, and 3, 14. C6H14. So therefore, these two guys, A and B, are isomers. Okay. The way to draw the condensed formula would be CH3, and then we can say C, CH32, CH2, CH3. Or in many textbooks, you'll find another option could be CH33. Sorry, I had a small mistake here. CH3, C, CH2, CH3. So most textbooks will consider the main chain this and these three guys to be attached to this carbon here. But this is also correct. I will accept both, okay? I want you guys to learn because you can see it in any textbooks, okay? It's like the same here as you could say color coding the in this case it would be the same, right? So when you have substituents on the ending carbon, you can consider the main chain this and then everything that is attached to the end carbon, just add it up like here, okay? For naming, yes, but again, it's all a matter of nomenclature and once on different annotations for writing this down. And I want you guys to be able to read the molecules in any textbook that you guys can access to. Okay. Most textbooks, for the matter of being easier to write it, we use this notation here for condensed formula. If you do this in an exam, I'll be okay. But I'd rather have you guys learning this. So the main chain, and then you can consider everything that is attached to the end carbons. And then I'm gonna finally give you a couple of things here. Um, so far, every single molecule, look at the carbon chains that I presented here. Every molecule that we have looked at right now had all single bonds. Carbon has 4 bonds. All these bonds are single bonds. However, carbons can also have double and triple bonds. Okay, so let's consider this molecule here. And let's do the molecular formula for this. How many carbons and how many hydrogens in this molecule? Seven carbons. So let's see. Let's look at the picture. 1, 2, 3, 4, 5, 6, 7 carbons. Okay, so that's correct. And then how many hydrogens do we have? Guys, how many hydrogens do I have in this position here?
One.
Right in this position here, I'm gonna show it with an arrow so everybody can see it. And I want everybody to look into this. How many hydrogens do I have in that carbon here? 0 hydrogens. Beautiful, okay? Because this carbon has a double bond to this carbon here, so that's 2 bonds already. And there is another bond to this carbon, and there's another bond to this carbon. So that's 4 bonds. So for hydrogens, we have 3 hydrogens here, and 3 hydrogens here, that's 6. 3 more here, that's 9, 11, 14. Okay? What about this molecule? How many carbons here? So 1 carbon here, 2, 3, 4, 5, 6, 7. So that's 7 carbons. And how many hydrogens do we have in this molecule, guys? More people? So anybody else can guess? Can you guys answer the question? How many hydrogens do we have in this last molecule? 10 hydrogens. 1 hydrogen here. So I'm gonna write the hydrogens now in red. So we have 1 hydrogen here. None here, that's 0. We have two hydrogens here. There will be one hydrogen here. And there will be three here and three here. And 0 here. Okay. Can I recount the carbons? I'm going to show the carbons with an arrow. Okay. So one carbon here. Another carbon here. Another carbon here. Every intersection is a carbon, remember. Another one here. Another one here. One here. And one here. So I'm going to color code the carbons as blue. Oh, sorry. Oh, so why is there no zigzag between the first two carbons? Because it's a triple bond. So whenever we do, and you will learn that, why is that later? Because that's the geometry of molecules with triple bonds. So whenever you guys, we draw a triple bond, we don't do zigzag. That's a very good point. Okay. So in that molecule, we have carbons are shown with an arrow. So 1, 2, 3, 4, 5, 6, 7. And hydrogens, we have 1, 0, 2 more here, 3, 4, 0, 7, 10. Okay, I'll show you some more examples during the next class. And I will try to make to leave you a set of problems on Blackboard. I'm not gonna grade them or anything, it's just for you to practice, okay? But guys, drawing properly organic molecules is a fundamental skill that I really want you to learn in this class. It's going to be one of the most important skills that I want you guys to learn. So when you go to organic, you know how to draw organic molecules really well. Okay. Any other questions that you guys might have for today? All right. So great pleasure to have you guys here today. Hopefully you learned something new. Um, and as I said, we will practice some more next class. I'll see you guys next Tuesday. And again, pleasure having you here. Have a great night. Enjoy the weekend, guys, and the rest of the week. I'll see you next week. Okay.